Hello everyone and welcome to Signal Systems and Signal Processing with Wolfram U. In this lesson, we will go over Fourier transform theorems. Given a signal x of t and its Fourier transform x of j omega, we would like to know what would be the Fourier transform of x of a times t, or a shifted version of x of t. Similarly, if we have differentiation in time, convolution, multiplication, and finally, we will study the Parseval's relation. The first theorem, the time shift theorem, says that if we have a shifted version of signal x of t minus t0, the Fourier transform in the frequency domain will be x of j omega times e to the power minus j omega t0. If we call the new signal y of t, then the Fourier transform of y of t will be y of j omega. If we use the formula for the Fourier transform, write out the integral, and then apply a change of variable called t minus t0 tau, the new integral will be as shown here. If we extract the constant term e to the power minus j omega times t0, then what we are left with is the Fourier transform of x of t. Note that the magnitude remains unchanged and the phase is shifted by omega t0. Let's look at an example and verify the time shift theorem by comparing the Fourier transforms of the two signals shown here, x of t and y of t. Looking at the plot of the two signals, you can see that they are a shifted version of one another. We can first find the Fourier transform of x of t and use the Wolfram language to also find the Fourier transform of y of t. We plot the magnitude and the phase of the two Fourier transforms. We can see that the magnitudes are equal and the phases differ by a linear term, and this proves the theorem. The next theorem says that if we have the scaled version of x of t, x of a times t, in the frequency domain, the Fourier transform will be 1 over absolute value of a times x of j omega over a. And in a special case, if we have x of minus t, the Fourier transform will be x of minus j omega. To prove this theorem, we can simply call the new function y of t and take the Fourier transform of y of t using the formula for the Fourier transform. And if we apply a change of variable called a times t tau, we can get to the expected result. We have to consider two different scenarios when a is positive and n b is negative, and that gives us 1 over absolute value of a for the coefficient. Time differentiation theorem says that if we have the Fourier transform of x of t, the Fourier transform of derivative of x of t with respect to t will be j omega times x of j omega. To prove this, we look at the derivative of x of t with respect to t. If we write x of t using the synthesis formula in terms of x of j omega, and then simplify the expression by taking the constant value 1 over 2 pi outside the derivation and take the derivative of x of j omega inside the integral, we will come up with that coefficient j omega. And that proves the theorem. Let's look at the second example. Use the time differentiation theorem to obtain the Fourier transform of the following signal x of t. You can look at the plot of x of t to see what it looks like and how it changes over time. Now, observe that this signal x of t is a derivative of the unit triangle. If you take derivative of unit triangle, you'll see that you get the signal x of t. Therefore, according to the differentiation theorem, the Fourier transform of the signal x of t equals j omega times the Fourier transform of the unit triangle. If you take the Fourier transform of the unit triangle, we get the Fourier transform of x of t. We can check our results by comparing this value with the Fourier transform of x of t directly, and they are equal. The next theorem is the time convolution, and it says that if we have two signals x of t and y of t, the Fourier transform of the convolution of the two signals x of t and y of t in time domain is the product of the Fourier transform of x of t and y of t, basically x of j omega and times y of j omega. This theorem is also proved by just simply applying the definition of the Fourier transform on the convolution integral. If we take the Fourier transform of the convolution of x of t and y of t and change the order of the integration and apply the shift theorem to the inner integral and call the inner integral the Fourier transform of j omega, what we will get will be the product of y of j omega and x of j omega, which completes the proof. Next, let's look at an example where we are given x of t and y of t, and we would like to use the convolution theorem to find the convolution of x of t and y of t. So basically, we will find the Fourier transform of each of these signals, and the Fourier transform of their convolution will be the product of the two Fourier transforms, and then we take the inverse Fourier transform to bring back the problem to the time domain. First, let's find the Fourier transform of x of omega, and then for the Fourier transform of y of omega, we can look at the Fourier transform magnitudes of the two signals. Now, looking at the product of the two Fourier transforms and applying the inverse Fourier transform, we get this function in time domain. If we compare the result with the convolution of x of t and y of t in time domain, we'll see that they are equal. Here you can find a plot of x of t and y of t and their convolution in time domain. The next theorem is called the time multiplication, also known as the modulation theorem. If you have two signals x of t and y of t, the Fourier transform of their product x of t times y of t in the frequency domain will be 1 over 2 pi times the convolution of their Fourier transforms. Consider two signals x of t and y of t as shown here. We would like to use the multiplication in time property of the Fourier transform to obtain the Fourier transform of the product of these two signals. Let's first find the Fourier transform of x of t, x of omega, and the Fourier transform of y of t, y of omega. According to the modulation theorem, the Fourier transform of the modulated signal is 1 over 2 pi convolution of x of omega and y of omega, or x of j omega and y of j omega. We can also plot the magnitude spectrum of the product function and see how it changes over the frequency. Next, we have the Parseval's relation, which says that if you have a signal x of t in time domain and the Fourier transform in the frequency domain x of j omega, the energy of the signal in time domain is equal to 1 over 2 pi times the energy of the signal in the frequency domain. So if you have the energy of the signal in the frequency domain, you can find the energy of the signal in the time domain. Let's look at an example. X of t is given as shown here. We would like to verify the Parseval's relation for this unit pulse signal. First, let's find the energy in the time domain. We take the integral of unit box squared, t going from minus infinity to plus infinity. That gives us 1 in time domain. Moving to the frequency domain, the Fourier transform of the unit pulse can be found as shown here. And if we find the energy in the frequency domain and multiply by 1 over 2 pi, we get the same answer. And this verifies the Parseval's relation. In this lesson, we went over some of the important Fourier transform theorems: time shifting and time scaling, time differentiation, convolution in time, multiplication, and Parseval's relation. We showed some examples with applications of the theorems in solving several elementary signal processing problems.